In Chapter 5, we're going to be studying a special distribution called the normal or Gaussian distribution. Our normal distribution is the most important of all of our continuous probability distributions and is used extensively for many statistical inference methods. It is the basis of quite a lot of our statistical analysis. So, what is the probability density function of a normal random variable? So the probability density function of a normal random variable is symmetric about the mean, mu, remember mean is our expected value, and has a bell-shaped curve. So we talked about mean as our expected value, and it has a bell-shaped curve. We'll see a picture of it momentarily below. So the normal distribution has a probability density function of the form f of x is equal to 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared over 2 sigma squared for all x, for all real x, depending on two parameters, the mean and the variance of the distribution, where our mean is mu and our variance is sigma squared, just like we talked about it before. The probability density function is a bell-shaped curve that is symmetric about our mean, and the notation to describe that x is distributed normally with a mean of mu and a variation of sigma squared is x with the tilde and then n for normal, mu sigma squared. We saw this very similarly with the binomial distribution where we had, for the binomial, there we go, x was distributed by a binomial distribution centered at the number of trials and the probability of success. So this is the way we describe how our random variable is distributed. When we looked at section 3.1, they were distributed due to the binomial distribution. This one is distributed via the normal distribution. So what does a normal distribution look like? Well, here we have two pictures. These figures show examples of normally distributed random variables. The graph over here on the left shows one distribution overlapped by another, but they're centered in different places. The one on the left has a mean of 5, and the one on the right has a mean of 10. But they have the same shape, same variance, same width, same height. That tells us that our variance is the same for both. And in fact, this one is a mean of 5, variance of 4, and the second one is a mean of 10 and a variance of 4. Versus if we look at the two distributions on the right, we still have our mean of 5 and our variance of 4. But what happens if we have a mean of 5 but a variance of only 1/4, so 0.25? Well, suddenly all of our distribution has to be smushed into this little area around 5 because it's not very spread out. Remember that variance tells us how far apart all of our data is spread, right? Our distribution, the spread of our data. And so having a variance of 4 is definitely wider than having a variance of 1/4. Given that we now know what the normal distribution looks like, let's talk about what a standard normal distribution looks like. The normal distribution that has a mean of 0 and a variance sigma squared of 1 is known as our standard normal distribution. This is one that comes up quite a lot. This is our standard normal distribution, and its probability density function for all real x, right? X is between negative infinity and positive infinity, is phi of x is 1 over the square root of 2 pi times e to the negative x squared over 2. And the CDF then can be found in the same ways that we found CDFs in the previous unit. We integrate. Not your favorite, I know, but you can follow along in this one. So the CDF for this one of our standard normal distribution then is capital phi of x, and we would find it by integrating from negative infinity to x our phi of y, which is our PDF, times dy. And we will signify that as our probability that x is between two values or x is less than or equal to small x. This isn't all that different than what we saw in previous chapters. What is really interesting about the standard normal distribution is it can help us describe something we call the empirical rule. And this is related to that Chebyshev inequality that we looked at previously. And it was an inequality. What the empirical rule says, well, now that we know the exact distribution of our data, and if we standardize all of our data to the standard normal, it'll be centered at 0 and have a variance of 1 or a standard deviation of 1. And what we can then describe is the exact percentage. Well, it's still approximate. It is still approximate in an ideal, perfectly normal data set, which in terms of experiments is still more of a theoretical. So as we approach a perfectly normal, right, we'll bring in some limits. We could say that the mean plus or minus 1 standard deviation is going to give us approximately 68% of our probability or 68% of our data results. Our mean plus or minus 2 standard deviations then covers 95% of our curve, right? 95% of the area under the curve. And our mean plus or minus 3 standard deviations brings us all the way up to 99.7%. So 95% of our data is within 2 standard deviations of the mean. And 99.7% is within 3 standard deviations of the mean. That means we have 0.3% or 0.15% on the high end out here and 0.15% on the low end here that are outside of 3 standard deviations away from normal. Those are some pretty significant results. So if we notice then our area down here, we notice that big phi of x, or our CDF, yields the left tail probability, P of x being less than or equal to some value that we give it little x, which means the probability that x is greater than or equal to x is 1 minus the probability that it is less than x, less than or equal, right? So again, we've seen that before. And so we're going to look at some results using the standard normal. So the CDF of the standard normal distribution is big phi of x, and it's tabulated, and I posted it in an Excel file. So the Excel file that is posted will give you what we call a Z table. And we're only going to use it for just this one problem until we learn other ways to find it. Okay? So let's look at the standard normal Z table in our Excel file to determine the following probabilities for the random variable z, which is normally distributed with a mean of 0 and a standard deviation of 1. So let's take a look. I've included a video here that's showing you how to find probability of 0.31. And that is our first one, our probability that z is less than or equal to 0.31 is just like the video shows. You go down 0.3 and go over to 0.01. And when we do that, we find out that we have a probability that is equal to the 0.6217 that is still boxed. So in terms of our distribution, we have our normal. I'd never draw this perfectly. Bear with me. Remember, it's centered at 0. So 0.31 would be a little bit past 0, right? We'll have 0.31. So it'll be all of this area here. So it should be more than 50%, right? At 0, it's 50%. So we are a little more than that. So we have 0.6217 is the area under that curve. But if we look at the second one where it says, what is the probability that z is greater than or equal to 1.05? Well, remember that probability that z is greater than or equal to 1.05 is the same as 1 minus the probability that z is less than or equal to 1.05. So we need to find 1.0, and then we'll move over to 1.0, and then over to 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. Or we get 1 minus 0.8531, which is 0.1469. And if we wanted to figure out what the probability is of z being between negative 1.5 and 1.8, then we have to look at this and remember that it has something to do with our definite integrals. So essentially, if you think about this one, what we're trying to do is we're trying to integrate from negative 1.5 to 1.18 our phi of x, right? So if we were to do that, we would find capital phi of 1.18 minus capital phi of negative 1.15. So we'd have big phi of 1.18 minus big phi of negative 1.5. And what ends up happening is we end up with 1.18 would be 1.1. We go over to 0.08, which is 0.8810. And in a similar fashion, you'll go instead to the positive z tab on the Excel file, go to the negative z tab, and you're going to find negative 1.5. And then it'll be negative 1.50. And so we end up there with a probability of 0.0668, or a total area of 0.8142. Our entire probability is 0.8142. You're probably thinking there has to be a better way than using an Excel file of z-tables. Well, of course there is nowadays. So the best part of this is you have free access to Excel through your student account, and we can use Excel. You can also use a TI-84 to accomplish the same task. So I'll write out how to do it on both. So we're going to repeat the same example. I'm going to do the standard normal distribution function in Excel using norm.dist to determine the following probabilities. So to find where z is now less than or equal to 0.31, we're just going to say, okay, well, that's big phi of 0.31, which we can find with norm.dist. We have to figure out what goes inside of the parentheses. So the way that Excel describes norm.dist is as x, comma, the mean, comma, the standard deviation, and then comma, is it cumulative? And since we're using big phi, the answer is yes for cumulative. So x is the value we're looking at. That's our 0.31. That is our probability that the probability we're trying to measure. So our x is 0.31. Where is our standard normal distribution centered? The mean is at 0 and the standard deviation is 1. Please note that a lot of the times we're writing out the distribution of a normal variable. It is as mean, comma, variance, whereas Excel is mean, comma, standard deviation. So you're going to have to take the square root of your variance to put it into your standard deviation in an Excel. The nice thing is you're already in Excel, so you can just say what the value is in one cell, the next cell down, just say it equals the square root. And now you have your variance. And when you put it in, you put in your x value, you put in your mean, and the standard deviation, you're going to say equals that cell. And then you say cumulative is yes. So you can find ways to use Excel to your best advantage here. Okay, so our normal distribution this time is centered at 0 and has a standard deviation of 1. And yes, this is cumulative. And when we do this, we end up with that 0.6217. So no need to look up a table. Excel does it for us, right? What else can we do? Do we have other options? The answer is absolutely. You can also use on a TI, you can do second, vars, and then you're going to look at number 2. So second, vars, and number 2. And what that's going to bring up is a normal CDF, which is what we want, normal CDF. And our options here would be that it goes from, and they don't really have a way to write negative infinity, so they just do -1 times 10 to the 99. So that's fine. And you put your lower bound, so because we want less than. So this is left tail, so we will go from negative infinity, right? This is negative infinity, to our upper end, which is x is 0.31. And our mean is 0, and our standard deviation is 1. So essentially, this is what it's giving us. And we will also get the exact same results. I can show you this in class on Monday if you want to learn how to do this with your calculator. It's really not terribly difficult. If I get a chance to do a quick video on it later, I will do that. How can we then use Excel or TI to find out the probability that z is greater than or equal to 1.05? Well, that is 1 minus the probability that z is less than or equal to 1.05, or 1 minus norm.dist of 1.05, 0, 1, true. Or we end up with 0.1469 again. We end up with the same thing. And can we do something in between? Can we say where is z between -1.5 and 1.8? The answer is yeah, definitely. We can do that. So this one, we're just going to have two different norm dists. So this one is going to be phi, a big phi, that is, of 1.18, or CDF, minus big phi of -1.5, which then is norm.dist of 1.18, 0, 1, sorry, 0, 1, true, minus norm.dist of -1.50, 0, 1, true. And you can do this on the TI by doing second vars 2 twice. So you can do it for the 1.18, and then you can say minus, and then you can do it for -1.5. But there's actually an easier way on the TI, and I'll show you that in just a moment here. So we end up with 0.8142. On the TI, you can actually make this one normal CDF. You can use normal CDF, and instead of negative infinity to 0.31, now we can do -1.5, up to 1.18, 0, 1. And it will give you the exact same answer. Sometimes I actually prefer the calculator to Excel, but I see pluses to both of them. Pick the one that works best for you. You'll have access to Excel for all of our exams and assignments for this unit and moving forward. So I will have some extra TI calculators with me in class that you can borrow if you want to practice on these too. All right, let's try another one. We can use our z tables, or we can end up finding out that we can use Excel to help us go backwards to find percentiles. So, for example, the 80th percentile is where big phi of x is equal to 0.8. We learned this with median, where we set it equal to 0.5, our CDF. We called it capital F then because we didn't have a specific distribution. And we also did it for IQR, where we set it equal to 0.75 and 0.25. So now we're just going to set it to a specific percentile that we're looking at. So we can find the x value then by reading the table in reverse. And we can see that phi of 0.84 is 0.7995, and the phi of 0.85 is 0.8023. So the 80th percentile will be somewhere in between them. And that feels uncomfortable to land in between. So instead, let's use Excel or the TI to figure this one out. So the TI, for the TI to do a normal inverse, we would do second vars and 3 this time. And it is inv-norm, so it's an inverse norm, right? An inverse norm. So if I wanted to do this with my 80th percentile, I would put in 0.8 for the percentile. I'm looking at 80th, turn it into a decimal, comma, the mean 0, standard deviation 1, and we want a left tail. And because we're looking at less than. Okay. How does this work on Excel? On Excel, we use the norm.inv command. So when we look at the norm.inv, we have to figure out what it's going to ask us again. And norm.inv, change my pen color here. Norm.inv is going to ask us for the probability, which is the percentile, the mean, and the standard deviation. And that's it. That's all we have to put into this. The probability we're looking for, the mean, and the standard deviation. So if we wanted to find the 70th percentile, right, this is the 70th percentile, then we would say, where is capital Phi of x equal to 0.7? Do you really want to type in that really long exponential every time into Desmos, graph them, and see where they interact? No, there's no need for that. There's no need to find that intersection. We'll just use Excel norm.inv. So this case, we would have x is equal then to norm.inverse of, and we're looking at 0.7, center of 0, spread of 1. And we end up with that x value being 0.5244. And again, you can also do this one in the TI, and this one would be inv norm, and you would have 0.701 and left. And you would find the same thing. If we wanted to find the 95th percentile instead, then we would say x then is norm.inv of our 0.95, centered at 0, standard deviation of 1, or x is 1.6449. So let's try with the Excel functions in one problem. So let's suppose that, that our variable z is distributed normally from a standard normal 0, 1. Let's find the probability that z is less than 1.34. So that one is just going to be norm.dist of 1.3401, and cumulative is true, or 0.9099. Where is it greater than? Negative 0.22. Well, that one we have to rewrite it as 1 minus the probability that z is less than or equal to negative 0.22, right? Which is 1 minus norm.dist of our negative 0.22, 0, 1, true, or 0.5871. What if we're looking at in-betweens? I will say this is where the TI is a little bit quicker because you can just put the two numbers in. But if we're looking strictly at Excel, this is going to be norm.dist of 0.43, comma 0, 1, and true, minus norm.dist of negative 2.1901 and true, which ends up with 0.664 minus 0.0143 for a total probability of 0.6521. So we can keep going. We have a few more of these. So our probability that z is between 0.09 and 1.76 would be our phi of 1.76 minus our phi of 0.09, which I think I forgot to write on the one above it. There you go. So this would be phi of 0.43 minus phi of negative 2.19. There we go. So this one would be norm dot dist of 1.7601 true minus norm dot dist of 0.0901 true, which is 0.9608 minus 0.5359 for a total probability of 0.4249. What we're going to find on part E is something really interesting. Remember that we said that our distribution is symmetric? Well, here we're going from a negative value to a positive value for our z. So this is phi of positive 0.38 minus phi of negative 0.38, or norm.dist of 0.3801 true minus norm.dist of negative 0.3801 true. And something really fascinating happens here is it's not exactly equal. You would think maybe they are, but it's not exactly equal because we think because it's symmetric, they must be. Well, remember, we're not thinking in those terms. We're thinking of all the probability at that point or to the left of it. So in this case, we're thinking if this is our 0 here, 0.38 would be here, all of this area, and negative 0.38 would be all of this area. And so what's left between them will be symmetric, but these numbers aren't going to be identical. So we end up with, for the positive 0.38, 0.6408 minus, and for the area left of or less than negative 0.38, we end up with 0.3520 for a total probability of 0.2961. So notice we've only used norm.dist. We haven't used norm.inv, which is the inverse. So that's our normal distribution versus our normal inverse. So the value then, now we can find the value for which of x for which the probability that z is less than or equal to x is 0.55. Well, that is where phi of x is 0.55. That tells us x is norm dot inv of 0.5501, or x here is 0.1257. We can repeat this again on parts G and H. So where is z greater than or equal to 0.72? Well, that probability where z is greater than or equal to x is 0.72, we're going to rewrite the probability here to being 1 minus the probability that z is less than or equal to x. And we know then that the probability that z is less than or equal to x is now our 0.72. So we just do 1 minus 0.72 or 0.28. And so instead now we need to find then that x is the norm.inv of our 0.2801. And we end up with x being a negative 0.5828. And the last one gets kind of interesting because we want to know the value of which of x, sorry, the value of x for which the probability that z is between negative x and positive x is 0.31. So this is going to be interesting. We have to do a little bit of legwork first. So we have the probability of z being less than or equal to x minus the probability that z is less than or equal to negative x. And that total is our 0.31. That means that we have phi of x minus phi of negative x is our 0.31. Well, that makes this is still phi of x minus, well, this would be 1 minus phi of x is our 0.31. Which means if we do a little bit of distribution of our negative, we get 2 phi of x minus 1 equals our 0.31, or phi of x is going to be 1.31 over 2, which is the same as 0.655. So when we want to find x, then x is now going to be the norm dot inv of this 0.655 centered at 0, standard deviation of 1, and we end up with x being 0.3989. So what happens when we're not talking about a standard normal distribution? Well, we're going to look at this in the context of an example. So can we compare winning events at the Olympics? Tiana Bartoletta turned in a 7.17-meter winning long jump at the 2016 Rio Olympics, which was 0.334 farther than average. Jorian Moores turned in a 1 minute 13.56 1,000-meter speed skating time at the 2018 Pyeongchang Olympics, which was 1.848 seconds faster than average. How can we compare the results when they come from different populations? We can see which one is more rare just by comparing them, and that way that we can compare them, even though one is a long jump, we're talking distance, meters, versus time for our speed skater. The answer is then we have to normalize all of our data and standardize it to a standard normal. That sounds like a lot, right? But it's not so bad. The answer here then is that we can transform them into a standard normal distribution using something we call a z-score for each athlete, right? So a z-score. All right, let's see here. That's our z-score. So what is a z-score? A z-score is the number of standard deviations the value of interest is above or below the mean. It's technically part of what we were looking at. when we were looking at those x values on the standard normal, we were looking at how many standard deviations away from the mean it was. So this strips data then of all of its units and allows us to compare different kinds of distributions, well, different data distributions, I should say, that are normally distributed. We can compare them even though they have different units. So how do I find my z-score? My z-score is x minus mu divided by sigma. Not sigma squared, sigma. So this allows us then to relate the probability values of any normal distribution to the probability values of the standard normal distribution. So in particular, we can relate these probability values to the cumulative distribution function v. So for example, the probability that x is between a and b would be the probability that a minus mu over sigma is less than or equal to x minus mu over sigma, which is less than or equal to b minus mu over sigma. So here we're looking at z at a, just our standard z, and our z at b. So we just changed the middle to z, and we can rewrite the probability of a minus mu over sigma as the standard probability, the probability on a standard normal of the value b minus mu over sigma minus phi of a minus mu over sigma. Because again, we are changing these into standard normal. So if we circle back to Tiana and Yorian, we can look at some of their data. Their means are given and their standard deviations are given, right? And then also, those are the mean and standard deviation of the distribution of all of the results they have for these events. And then we have our particular athletes and how they scored. So we want to find the z-score for each athlete's outcome, which is the number of standard deviations that each is away from their respective means. So let's do the long jump. So our z-score for the long jump would be the x that was scored, right, which is 7.17, minus the mean, which is 6.836, divided by the standard deviation, which is 0.218. And that is meters minus meters divided by meters, which in the end is meter over meter, which is now unitless, which is exactly what we were looking for. And we get a z-score for the long jump of 1.5321. So this z-score says that this result was 1.5 standard deviations above normal. Let's see how our speed skater did. So our z-score for a speed skater is, well, this one we're going to have to do a little bit of adding up some time. It's 1 minute and then 13.56 seconds. So what we're going to have to do is say that this is 60 plus 13.56 or 73.56 seconds. Because if you notice, our standard deviation is given in seconds. So we're going to convert everything to seconds. So we get 73.56 minus the mean, which is 1 minute 15. So that's 60 plus 15.408 or 75.408. So we're going to get 73.56 minus 75.408. And then we're going to divide it by our standard deviation of 0.941. Or a z-score that is a negative 1.9639. Or a z-score that lands our speed skater 1.96 standard deviations below the mean. So if we were to do this in Excel, right, we would just use norm dist. Okay, so we can do this. So if we wanted to find our z-score for our long jumper, what is the probability here then, right, of z being greater than 1.5321? Let's find it. Now, we're finding our probability here. Probability that our z is bigger than 1.5321 is going to be this is the probability of beating, right? Of beating Tiana's result. That one would be 1 minus norm dot dist of 1.532101 true, which would be 1 minus 0.9374 or 0.0627. So there is only a 6.3% chance that someone could beat Tiana's score. Or not score, I should say, her jump distance. Well, let's look at Yorian here. So for our speed skater, the probability of beating our speed skater is going to be a little bit different because we don't want a number bigger. We want a number smaller because think of the difference. Long jump, we want it to be longer or greater than the mean. We want to be well over the standard, right? Well over what that average is, the expected outcome. Versus for speed skating, we want to be faster, which means our time is actually lower. So for a speed skater, we want the probability of someone getting a z-score that is less than or equal to negative 1.9639, which means they are doing it even faster than Yorian. So this would just be our norm dot dist of our negative 1.963901 true, which gets us a 0.0248 probability, meaning there's only a 2.5% chance that someone could speed skate faster than Yorian, which tells us that Yorian's speed skating performance was a little more uncommon or unusual than the long jump. Both of them are still exceedingly impressive. Yorian just happened to make his a little less likely to beat than Tiana's long jump. So can we use Excel then to find these same probabilities without having to find z-scores and without having to normalize their scores? And the answer is yeah, we can. So this is kind of cool. You can also do for the long jump here, we can just do the probability that z is greater than or equal to 7.17 meters, which is going to be 1 minus the probability that z is less than or equal to 7.17, or 1 minus norm dot dist. And now, instead of putting in the z-score, we're going to put in our 7.17, where our mean was the 6.836 and our standard deviation was the 0.218, and we still want true. And we end up with our 0.0627. If we do the same thing for Yorian and his speed skating, the probability of getting a time less than or equal to 73.56 is going to be norm dot dist of 73.56, comma, our mean, which is 75.408, comma, our standard deviation, which is 0.941, and true. Or we get our 0.0248. So we have options. We can standardize, or we can choose to just enter the data as it's given. So let's talk a little bit on our normal distribution here one more time. And this is just a way to wrap up the empirical rule I mentioned earlier when we looked at our standard normal. And there's a probability of approximately 68% of that our normal random variable takes a value within one standard deviation of the mean, 95% within 2, and 99.7% within 3. So we're going to look at an example using our empirical rule. So this one says That 3 weeks after planting, the heights of tomato plants have a mean of 29.4 centimeters, so there's our mean, and a standard deviation of 2.1 centimeters. If the plants are then taken to be normally distributed, find out the heights of approximately 95% of the plants using the empirical rule. Well, that would be 95% is mean plus or minus 2 standard deviations, which would tell us then we have the mean minus 2 standard deviations to the mean plus 2 standard deviations. Or we get 29.4 minus 2 times 2.1 to 29.4 plus 2 times 2.1. Or we end up with, just realized I was using parentheses and I meant brackets, or we would go from 25.2 centimeters up to 33.6 centimeters. These should feel very much like our trebuchets, where these shouldn't be too taxing. The height of exactly 95% is going to be a little different, right? So approximately 95 versus 95 exactly. So let's talk about 95 exactly. What does that look like? If we think about our distribution, right, we have, here's our mean, and within 2 standard deviations, we have 95% of our data. What that means is in each tail, I have what's left over. So if I have 5% left, then I have to split it over the 2 tails that are symmetric. So 2.5% ends up in the left tail, 2.5% ends up in the right tail. So what's kind of cool here is then we can say that we're looking at a value that we're going to call alpha. Okay, alpha is going to be 1 minus the 0.95, which is that 5% that we're going to split into 2 tails. So z of alpha over 2, which is again just one tail, is going to be the same as our z at our 2.5%, which as a decimal is 0.025. And we're going to find that by using our norm dot inverse of our 0.025 and our standard normal 0.1. And this gives us a negative 1.96. Or we can do a norm inverse here. There's another way you can do this one is you could also do that you want where 97.5%, right? You could do the top two, up to the top 2.5% there. So you could do it a couple of different ways. And so what we're going to say then is our exact 90, right? Our exact 95% then is going to look like mu plus or minus z at alpha over 2 times our sigma. So in this case, it's actually going to be 29.4 centimeters plus or minus our 1.96 times our 2.1, or in this case, the exact value is 25.284 centimeters to 33.516 centimeters. So our approximation using the empirical rule wasn't terribly far off. It was pretty close. If we wanted to do this for 90%, well, then we have to think about what's left over. So if we did 90%, right, if we have 90%, that leaves us with 5% in each tail, right, to add up to our 100. So in this case, we have to find our z of 0.05. So if we look at z here of 0.05. So we have our alpha would be 1 minus 0.9, which is 0.1. So our z of 0.1 over 2 would be our z of 0.05, which we already just said we needed, which is going to be our inverse norm, right? Our inverse norm, our norm inverse. So it's different on the TI versus the Excel. So if I do it the wrong direction, sorry. So if we're looking for our norm inverse of 0.05 of our 0.1, we end up with a negative 1.645. And so if we wanted to find mu plus plus or minus 1.645 times sigma, we end up with 29.4 plus or minus 1.645 times our 2.1, which gets us out to 25.946 centimeters to 32.854 centimeters. And last but not least, what is the probability that a tomato plant height is between 28 and 31? So here we're just doing our probability that we have a 28 is less than or equal to x, which is less than or equal to 31, which would then be the probability that x is less than or equal to 31 minus the probability that x is less than or equal to 28. And this is where not standardizing your normal distribution helps a lot. So we could do norm dot dist of 31, comma, mu, which is 29.4, comma, sigma, which is 2.1, and true, minus norm dot dist of 28, comma, 29.4, comma, 2.1, comma, true. And we end up with 0.7769 minus 0.2525 for a total probability of 0.5244. So we have a 52.44% chance that our tomato plant, if we were randomly to choose one, is between 28 centimeters and 31 centimeters in height after 3 weeks of planting, or 3 weeks after planting. So make sure that you either download and print off assignment 9 and work on the paper, or you can write it on your own notebook paper and bring it in on Monday.